Hey there, guys, you did it. We have done it. We have done our entire quarter of organic chemistry in a week less, online when we weren't planning to be online, and during a pandemic. I think, honestly, we should all be really proud of ourselves and all that we've accomplished. So let's talk about our week 9 summary, what we covered, what happened, and what to expect in our final bit of time together. So last week I showed you guys this meme, I see macromolecules, because they're everywhere. And we explored kind of the last 3 this week, lipids, proteins, and nucleic acids, and did carbohydrates the week before. So we're looking at these large biological molecules, which really gives us an opportunity to review for our final, because we're looking back on that chemistry, the organic chemistry that we've been studying, the functional groups, the chemical reactivities, all of that, the linkages we're seeing again in terms of the biomolecules, because these are all organic molecules, lipids, proteins, nucleic acids, and carbohydrates. So hopefully this also helps prep us for the final as we're constantly reviewing those functional groups and those chemical reactions. So highlights from the week are really that's all, folks. We finished it, where we wrapped up our content. So that means we went through all of our learning objectives. There'll be no new learning objectives. We did our last lab, or you're about to if you haven't already. We've done our last discussion. So really our highlight is just hitting that end point where we're done covering new content, and we're done reviewing and practicing that new content. And now it's that culmination looking back. So I want our learning outcomes for the week. They're a lot on the one hand, but I don't know if they're at that much more than a normal one. We always cover a lot, moral of the story. But you can see, like, if you look at these, we have several right here. So this is looking at chapter, I believe, 17. So we didn't cover chapter 17 in full. So use your learning outcomes to really find out, what do I need to know for the Unit 4 test? What do I need to know for the final? Because we didn't cover that chapter in full, just like we didn't cover the chapter on proteins in full. You were only assigned a portion of that to read, as you know from looking at those learning outcomes, and then just a portion of nucleic acids. So we're just kind of skimming the surface. And we could spend, biochemistry can be its own undergraduate degree. So we're just kind of touching on them and getting a good introduction into them. Let's talk our discussion questions a little bit. Compare and contrast butter and olive oil, the macro and then the micro level. So we're probably all at least a little bit more familiar with butter and olive oil. Whew, I gotta sneeze. Never mind, it passed. So butter and olive oil have some definite similarities and some definite differences at the macro level. So butter is a solid, or at least solid-ish, at room temperature, whereas olive oil is a liquid at room temperature, so we see a really critical difference. They both have a very oily or greasy feel, and we know neither will dissolve well in water, and if you need to wash either butter off your hands or olive oil off of something, you're going to need something like a soap molecule to help you out with that. So they have some distinct macro level similarities and differences. What about at the micro level? So at the micro level, one of their similarities is that both of them are triglycerides. So that means they're both made in a really similar manner, in the sense of that glycerol, the alcohols of the glycerol reacting with a fatty acid. And a fatty acid, you'll remember, is a long chain carboxylic acid. And when a carboxylic acid or its derivative react with alcohols, we get an ester. That's an esterification reaction. So this happens 3 times, so 3 similar or different fatty acids, and that's where we get our triglyceride. So tri, from the fact that 3 fatty acids, or we could think of it as tri, there's 3 ester linkages. And then the word glyceride is from the fact that the alcohol is derived, and they're linked then together by that glyceride backbone from that alcohol glyceride. So there's our similarity. They're all going to be classified the same way, and then we can even link that then to the macro level. This is why they're greasy and oily, because that is really mostly a pretty non-polar molecule. The smaller polar portions that we see aren't enough right there to counteract all of this non-polarity that we do see. So then how do they differ at the micro level? It really comes down to the saturation of these fatty acids, and that then is what leads to what we see, that solid at room temperature or liquid at room temperature. So fatty acids, so our long chain carboxylic acids here, can be classified as being saturated or unsaturated, whether or not they have a double bond or no double bonds, being fully saturated. And that changes how close together they can get, which impacts their intermolecular forces. And what we see is the more unsaturation that we have, the more double bonds in those fatty acid chains, the less close those big triglyceride molecules can pack together. And that means weaker intermolecular forces, specifically those London dispersion forces. So lower melting points. And if you have a lower melting point, you melt at a lower temperature, maybe room temperature, you've already melted. And so we see that with the olive oil. So by the fact that olive oil is a liquid at room temperature, we could predict that it has highly unsaturated fatty acid chains. And if we wanted to test that out, we could maybe do a bromination reaction and see how much bromine it took. Adding bromine to it and the color instantly disappearing as it added across that double bond. So linking it back to our Unit 1 content. So here is a bar graph that shows some of the different fatty acids that we find just in butter. So you can see butter is not, the fatty acid chains in our different triglycerides is not just like one or two. There's a lot of different ones that can potentially be there, and different butters from different places might end up having different fatty acids incorporated into them. So you can see oleic acid, myristic acid, etc. And not that you need to know this like off the top of your head, I kind of confirmed. Out of all of these, only 3 of them contain double bonds. So what that means is that the vast majority of these, so oleic acid actually does contain a double bond and does make up a lot of it, but the rest we see is saturated. And now if I couldn't find a good comparable graph for olive oil, but if we were to look at olive oil, what we'd find is that, yeah, there are a few fatty acid chains in olive oil that are saturated, but we have a reverse in that the majority of them are unsaturated or even polyunsaturated. We have multiple double bonds in the same fatty acid. And so the more unsaturation, the more double bonds that we're going to have in these triglyceride molecules, the more likely it's going to be a liquid at room temperature. And then, of course, the harder that fat is at room temperature, the more likely it is to be saturated versus unsaturated. So butter is actually pretty soft at room temperature because it does actually have quite a bit of unsaturation, just not enough to fully liquefy it like olive oil does. And so industrially in food science, sometimes we need to manipulate that, or we want to manipulate that, and so we will hydrogenate the fat. But there are some health consequences to that as well, which you read about a little bit this week. So our next discussion question, what's being shown in this image? Explain and describe in as much detail as possible. So just looking at the picture, it seems to be showing a quaternary structure of a protein. So it's a protein, and it's specifically, we're looking at, on the large scale, its quaternary structure. Not all proteins have quaternary structures. Some proteins just, their shape is determined up to the 3rd structure, and then they're good. But some proteins, like the one shown, end up being actually multiple smaller polypeptide units that bond together to create the larger protein's shape. And the reason we can probably conclude this is a quaternary structure has to do with the different colors. We've got like a blue and kind of a yellowish color, so I'm assuming those are then 2 different polypeptides. So then going further in a little bit more detail, those polypeptides, their general shape, that's the tertiary structure. The tertiary structure of a protein is that folding pattern due to the interactions between the R groups of an amino acid that determine the overall shape of the protein. So maybe R groups on different amino acid residues end up being attracted all the way across a polypeptide chain, and that can be like an ionic bond, it can be just hydrogen bonding, it can be non-polar things dissolving and interacting together, or it could even be, in that rare case, I don't think it's rare necessarily, maybe just that unique case of a covalent bond can form, that disulfide bridge, and that links and folds and bends the protein into that really specific tertiary shape that maybe also links with another polypeptide to make like the quaternary that we see. We can also see, I think, some alpha helices in here. Got some of those nice, they remind me of those old telephone cords that are part of the secondary structure. So those don't come about by interactions of our groups. Those are determined, those come about by the by hydrogen bonding. We can't see the primary structure, but we can infer that it's there. So finally, what are the base pairing rules for nucleotides, and why and how do they exist? You probably know the base pairing rules from your biology classes, or if you haven't taken them, you know, they're fairly straightforward. A bonds with T, G bonds with C. If we're talking about RNA, A bonds with U, uracil. I think it's interesting to look at the chemistry of why that happens, and it's actually really simple. And this got explained in an earlier video this week too, our Zoom session. It's kind of a puzzle piece fit in the A and T, as you can see in this picture here, fit together by 2 hydrogen bonds because of the anti-parallelism of the DNA strands. They just line up in that 2 to 2. You know, I've got 2 spots for hydrogen bondings, you have 2, so it works out perfect. Whereas guanine and cytosine have 3. And so it's a basic puzzle piece thing. And I just think that's really interesting, as I shared in the Zoom help session video, so I don't want to spend more time on that. What's next? Well, the end. The end is coming. So it's finals week, or really we have, you know, technically we have last day of instruction is Tuesday, and then we move into our 3 days of finals week before the end of our quarter. So that's what we should be preparing for in the next bit. What should you be doing? Make sure to take your Unit 4 test. It opened on Friday and it closes on Tuesday. And you're welcome to wait all the way to Tuesday to take it, because you're not missing out on any content before that. So you do you on what works for your schedule. Make sure to look at the Week 10 overview page. I made sure to post it earlier this week so that you had lots of time to be reviewing it and being like, okay, what's coming up? Because I know you guys have those kinds of questions right now. What's our last week? What does finals week look like for this class? So there is an extra credit opportunity for the class described therein. That is new. I just added that today. So if you looked at that earlier, you're going to want to go back and revisit that. I have the Zoom Kahoot review that will play on Tuesday at 10 to 11. Thank you for those of you who sent me the times that worked out best for you. I know that there was no way to schedule a time that worked for every single student in the class, so I just had to kind of cast a net that would hit the widest amount of people. So I hope to see many of you on Tuesday for that, and there's instructions on that in the review as well, or in the Week 10 learning outcome stuff. And then your final exam, there's 2 parts to it, a part A and a part B. You don't have to take them back to back. You don't even have to take them on the same day. And again, I'm not going to spend too much time here because that's all described in the Week 10 overview page. But make sure you read that early in the week. And if you don't understand or you have questions about what's going to happen, let me know so that I can get those. I don't want you to be stressing about that. And in terms of prepping for your final, I don't have a specific study guide. A big part of the reason for that is because I have given you detailed study guides for each unit, so you already have an idea of what was important along the way. But I know that that can be like, wow, we covered so much, and we really did. You know, do think about big picture items, things that we've repeated along the way over and over and over. So we've constantly talked about naming. We've constantly talked about physical properties and relating that back to polarity and hydrogen bonding. We've looked at several, chemical reactions, especially that link up different things. How are alcohols related to alkenes? How are carboxylic acids related to esters? How are amides related to carboxylic acid? So those, like the big picture items. And I know that that's easier for me to say, like, you just study the big stuff. But I, that's a good skill as a student to start developing, is looking back over my material. How can you identify that stuff? So good luck this week, you guys, as you are preparing. The end is, we're so close. We can do this. Just a few more days.